Good day, fellow colleagues and lecturer. This is Precision Engineering Solutions, consisting of myself, Matthew Ricketts, Kenroy Henry, Malicke, Jerome Samuels, and Najay Nelson. Let us get into the scope of this project. The scope of this project is to design and develop a high-precision instrumentation circuit for Ricketts Limited that converts strain gauge resistance changes into a measurable voltage for structural testing. Now, we have 6 objectives for this project. The first one being to convert resistance into voltage. So we must design the circuit to turn strain gauge resistance changes into a measurable voltage. Our second objective is to minimize noise. So we must filter unwanted electrical noise and environmental interference. Our third objective is to compensate for temperature. So we must ensure the circuit works accurately despite any temperature changes. Our fourth objective is to amplify the signal. So we must boost the strain gauge signal to fit the data system's input range. Our fifth objective is to ensure stability and accuracy, making sure the circuit provides stable and accurate readings under varying conditions. Lastly, our last objective is to optimize the power usage. So our circuit must be able to use low power for operations in remote locations. So here is the schematic diagram my colleagues and I have designed in order to achieve these objectives. We will be going into the schematic diagram section by section, starting with the power supply. So, the Wheatstone bridge and the amplifiers require a stable DC power supply. With this reason, we have decided to go with the 5-volt power supply. We will now go into the Wheatstone bridge, which will be covered by my colleague Kenroy Henry.
Well, thank you for that one presentation. I will now continue by presenting on the full-strain Wheatstone bridge. Now, the Wheatstone bridge system is a cornerstone for precision measurement that is widely used in engineering application to detect strain and small resistance changes. Now, let's explore the components and functionality of the full-strain Wheatstone bridge. The full-strain Wheatstone bridge is a circuit configuration consisting of 4 resistors that are arranged in a diamond shape. This configuration is specifically designed to ensure small changes in resistance and temperature caused by external forces. In the full-strain Wheatstone bridge, it consists of 2 resistors that experience an expansion, which increases the resistance, and 2 that undergo compression that decreases their resistance. This opposing behavior amplifies the circuit system and create a change in the resistance and cause an imbalance in the circuit that will produce a small output voltage that is ideal for high precision and reliability. The full-strain Wheatstone bridge consists of the following components: 4 standard 120 ohm resistors that is used to detect small changes accurately and maintain balance in the system. A 5-volt excitation voltage which provides the circuit with power, and a reference voltage to detect imbalances within the system. This combination of precision resistor and consistent excitation voltage is critical in delivering high sensitivity required in the strain measurement application. Here's how the full Wheatstone bridge system works. There's a balance state where all resistors are equal and there is no voltage being sent within the circuit. Now, when a force or strain is applied, it causes 2 resistors to expand, which increases their resistance, and 2 to compress, which decreases their resistance. This imbalance causes a small voltage output to be produced, and this voltage output is then applied to the circuit, causes a strain, which serves the system with a signal for further processing and measurement. Now, this voltage is sent through the circuit and ends up to the data acquisition or the microcontroller, which gives a force reading or a strain that is used to give high accuracy and efficient measurement or for physical changes. Some advantages of the Wheatstone bridge that it provides high sensitivity and accuracy, and it helps to detect even the minute changes in resistance. It is a trusted system that is used in a wide range of applications and fields within the engineering systems such as aerospace engineering, civil engineering, and also factories. To sum it up, the Wheatstone bridge is a reliable circuit used for precision measurement for the smallest change in resistance that is used in a real-world application, and is a critical tool for engineering solutions. I now hand over to my colleague.
So moving on to the signal conditioning aspect of this circuit, we're using the instrumentational amplifier INA333. As we know, instrumentational amplifiers are very high gain and precise devices which are well suited for this kind of circuit. They amplify the difference between 2 input signals, and they also reject any signals that are common to both inputs. The way we have it configured right here is based on the data sheet from the manufacturer. 2.5 volts is being used as a reference voltage, and the potentiometer R3 is being used to set the gain of the instrumentational amplifier. For the strain to resistance conversion, the equation is the nominal resistance multiplied by the gauge factor multiplied by the strain. That gives us the change in resistance. So for the smallest detectable strain of 10 microns, we get 0.0024 ohms. For the maximum strain of 1000 microns, we get 0.24 ohms. Now we convert this to voltage and get the voltage difference. So for the voltage output at the strain gauge, for the smallest detectable change, it's equal to the voltage across the Wheatstone bridge, which recall was 3.3333, multiplied by the nominal resistance being divided by 240 plus the change in resistance, which as we remember is 0.0024. So that gives us a value for VDC2 at 1.66665000017 volts. For the reference voltage output, VDC3, we get 1.6666, etc., 7 volts. And the difference between them, VDC3 minus VDC2, would be 16.66665 microvolts, which is going to be significant for an amplification equation. Now I'm going to hand over to my partner Najay. He's going to explain those calculations as well as some more characteristics of instrumentational amplifiers.
Okay, thank you, Jerome. I'll be taking it from here. My name is Najay Nelson, and today we're just going to be going into the amplification of the circuit. Now, so once we take that output from the maximum and the minimum stress, we simply put them into the equation VO equal VI plus K plus C, where VO, we put our desired voltage, and VI is the input voltage we obtain from the Wheatstone bridge circuit. So simply take both equation 1 and 2 and solve simultaneously for K. Once we obtain K, we can solve for C. In this case, C can be approximated to 0, as what we'll really be needing here for this instrumentation amplifier is the gain for this circuit to achieve our desired output. Now, using the formula provided to us by the manufacturers on the data sheet of the instrumentation amplifier, we can solve for our gain resistor, which we found to be 33 ohms. Now, we'll just simply use a potentiometer to achieve this type of resistance, as this is not a standard. Now, we'll be just going into the features and showing you how we have the perfect tool for the job. So we'll be going over the criteria and how the features of the INA 333 amplifier achieves our criteria. So first, going on to the first one, we have low input noise. Now, the term low noise in this context refers to specifically to the low input referred noise of the INA 333. This means the amplifier itself introduces minimal noise into the signal path, ensuring that the small signals from the strain gauge are not drowned out or distorted. All right, so which is really crucial. As we said, no distorted, get the precise signal what we need, and nothing added, or minimal added, as we say. If it was a perfect world, nothing would be added. I digress. So now we'll be going into the high common mode rejection ratio. Now, putting this in context, now imagine the instrumentation system installed on a metal bridge near a high voltage power line. The power line induces electromagnetic interface in the strain gauge wire. This noise appears as common mode signal on both input wires. So the input wires going into the instrumentation amplifier, just to clarify. The INA 333 with its 100 decibels common mode rejection ratio suppresses this common mode noise, ensuring that only the small differential signal from the strain gauge is amplified and sent to the digital acquisition system. So as a result, we get accurate strain measurements without interference, even in high noise environments. All right. Next, we'll be going into the temperature compensation, or also known as temperature stability. As an example, the bridge the instrumentation system is attached to experiences a swing from freezing conditions at night to hot midday temperatures. So many amplifiers would experience significant offset drift, requiring recalibration to maintain accuracy. However, the INA 333 with its offset drift of only 0.1 microvolts per degrees ensures consistent output despite the large temperature variation. As a result, reliable strain measurements over time without frequent maintenance or recalibration, saving you, the customer, time and money. Next, we have more features to go into. We'll be going into the linearity and stability. Linearity speaks as itself. As the strain gauge increases, we want a linear increase, and we have a stable gain settings with internal resistors which are incorporated within the instrumentation amplifier. Now, without us having to say incorporate any external resistors other than the gain resistor, this ensures great stability and linearity. So last but not least, we'll go into the low power consumption. So for remote bridge monitoring system powered by solar panels or batteries, energy efficiency is critical. Traditional op amps with high power consumption could drain batteries quickly or require larger, more expensive power systems. So the INA 333 draws only 50 microamps of current, making it ideal for low power and long-term operation, which is very crucial. As a result, a more sustainable and cost-effective monitoring solution, especially for remote installations. This concludes my part. I'll be passing it on to my colleague.
Okay, thank you very much, Najee. Now, I'm Malicke, as previously mentioned, and I'll be dealing with the filter aspect of the strain gauge circuit. Now, the filter is very, and I mean very, very critical to the overall operation of this circuit. Now, you might realize here that we're using a low-pass filter. Now, why a low-pass filter? Well, it's simple. Within strain gauges typically measure structural deformation or slow mechanical changes. And these changes normally occur within a certain frequency on the lower spectrum. Now, we chose a cutoff frequency of 100 Hertz, and this frequency is typically industry standard for strain gauges around the world. And so we chose 100 Hertz. Now, it is also key to know that the strain gauge typically will be placed in the open environment. So there will be other things such as electrical noise, heavy machinery, motor vehicles, and things of this sort, things in nature, in the environment, that can and will contaminate the signal integrity. Now, in order to prevent that, we utilize a low-pass filter. Now, with that being said, you might realize here within our circuit that we have a 100 kilo ohms resistor within our filter. Now, this is by design also to help and get the 100 Hertz, but more importantly, it is because a high resistance of this sort introduces a high impedance within the circuit. Now, why would you want to introduce a high impedance within the circuit? Well, a high impedance within the circuit means that, well, first and foremost, let's set this precedent. Strain gauges typically have high output impedance. And in order to maintain the integrity of the signal, we will have to match it accordingly. So hence, by introducing a very high resistance by means a high impedance, we are now preserving the integrity of the signal. This is important in order to have accurate measurements of these strains. Now, without accurate measurements, we cannot accurately build a product that will work to the characteristics of an actual top-end strain gauge. Now, with that being said, having done that, it's also key to know that the DAQ does operate with a certain impedance. So, having this impedance from the circuit, within the circuit, the high output impedance from the strain gauge and the high input impedance that is now introduced from the filter helps with the impedance that is necessary or the operational impedance for the DAQ. Another reason for a high impedance within the circuit is to help with the power consumption. Now, at the beginning of our presentation, you saw we had optimal power uses. And if we have a high impedance, then the amount of draw that it will draw from the current source will be significantly less than it having a very low impedance. So with that being said, this was just our design for a low pass filter. And if there are any questions, here I have 3 other benefits of a low pass filter. We already said the signal integrity, thermal noise reduction, signal smoothing. And if we have any more questions pertaining to this part of the circuit or the rest of the circuit, then feel free to reach out to us or email us, and we will get back to you with answers. Thank you for listening and being a part of our presentation, and we do hope that you sincerely did learn something from us. Take care.